Hi, my name is Vicky Espinoza. I'm a PhD candidate at UC Merced and creator of Cali Water Ag. Cali Water Ag is a trilingual YouTube channel that aims to foster a better understanding of the science and policy behind California's water and land use. This is Cali Water Ag's Water Issues in Underserved Communities in the San Joaquin Valley 3-part series. In this second video, we will go over drinking water sources and issues. In this video, we will go over what are the domestic water sources for underserved communities in the San Joaquin Valley, how domestic water is served, and drinking water challenges. Most unincorporated communities are served by groundwater. That is about 87% of community water systems in the San Joaquin Valley. There are two types of water systems in which water is sourced to underserved communities. The first being private wells, where each home has its own well and well owners are responsible for the upkeep of their wells. Then there is water served to communities by community water systems, in which homes are connected to a central well and associated treatment systems. The prevalent drinking water challenges that underserved communities deal with to this day are water quality, water supply, and unaffordable costs. To place the San Joaquin Valley's drinking water issues into perspective, let's go over some facts. There are about 64,000 people in 64 disadvantaged unincorporated communities, or DUCs, that receive unsafe drinking water. During the 2012 to 2016 drought, the state received more than 2,500 domestic well failure reports, most located in the Central Valley, which highlights the need for climate change adaptation strategies that address the needs of underserved communities as well. Failing groundwater levels are likely to leave up to 12,000 additional wells dry, impacting up to 127,000 people's primary source of water. Drinking water issues disproportionately impact low-income communities and communities of color. Drinking water quality issues in San Joaquin Valley's rural communities have persisted for decades. Some of the most common contaminants present in groundwater sources are nitrates, arsenic, 1,2,3-Trichloropropane or TCP, Dibromochloropropane or DBCP, and Chrome 6. Common surface water contaminants are mostly agricultural and industrial byproducts. Let's dive into some of the impacts of groundwater contaminants on underserved communities' drinking water source and health. Nitrates are a very prevalent contaminant in community drinking water. 97% of wells sampled in the San Joaquin Valley contain nitrates as shown by the red dots on the map. The maximum limit of nitrates in drinking water, as stated by the California Department of Public Health, is 45 milligrams per liter and 10 milligrams per liter as nitrogen. According to a report by Community Water Center, 20% of small public water systems deliver water with high nitrate levels that exceed federal limits. Nitrate can come from excess manure and fertilizer that runs into groundwater, contaminating the source of water, and can cause algal blooms in surface water. Nitrates disproportionately impact women of color in the San Joaquin Valley, often leading to double the state rate in miscarriages, and leads to 2.5 higher than average cases of sudden infant death, or SIDS. Nitrates in drinking water sources also leads to blue baby syndrome. Detecting nitrate in water is difficult without a water testing kit, since nitrate is colorless, tasteless, and odorless. Nitrates are more often found in groundwater than in surface water, and are more common in shallow wells in agricultural regions. If you are a community member in an underserved community in the San Joaquin Valley, I recommend contacting a community organization like Leadership Council, Self-Help Enterprises, or Community Water Center so that they can direct you to the best local resources. Studies have found that there are higher arsenic levels in community water systems in underserved communities. The maximum limit of arsenic in drinking water is 10 micrograms per liter. The map shows wells with arsenic concentrations less than 9.9 micrograms per liter in yellow, 10 to 49.9 micrograms per liter in orange, and greater than or equal to 50 micrograms per liter in red. The wells in orange and red exceed the arsenic maximum limit. Arsenic naturally occurs in groundwater, soils, and sediments. The overpumping of groundwater causes arsenic stored in deeper soils to be released and leached into the aquifer. Arsenic-contaminated groundwater is then used for drinking water or irrigating crops. These are crops that make it to our dinner tables, which makes it all the more important to properly wash our fresh fruits and vegetables, test our groundwater, and address groundwater overpumping now with future generations in mind. High arsenic exposure could cause cancer, heart disease, diabetes, and has been known to impact the utero, lead to increases in infant mortality, and impact cognitive development in children. 1,2,3-trichloropropane, or TCP, is a man-made chemical and is highly present in industrial or hazardous waste sites. There are also pesticides that contain 1,2,3-TCP. The maximum limit of 1,2,3-TCP in drinking water is 0.005 micrograms per liter. Contact with 1,2,3-TCP can cause irritation and burn the skin and eyes. Breathing 1,2,3-TCP can cause irritation to the nose, throat, and lungs, headaches, and affect concentration, memory, and muscle coordination. Long-term effects of exposure can lead to liver and kidney damage and cancer. When 1,2,3-TCP comes in contact with water, it dissolves and sinks to the bottom. The most common way contamination removal professionals remove 1,2,3-TCP from groundwater is to filtrate it using activated carbon. Please do not attempt the removal of 1,2,3-TCP yourself. Contact a remediation specialist for help with any groundwater contamination issues. Dibromochloropropane, or DBCP, is a man-made chemical and was extensively used in pesticides. DBCP was banned in the United States in 1979. The maximum limit of DBCP in drinking water is 0.2 micrograms per liter. The map shows active and standby California Department of Public Health wells that have DBCP levels higher than 0.2 micrograms per liter. Exposure to DBCP can cause gastrointestinal distress, pulmonary edema, and acute inhalation can impact the central nervous system, kidney and liver, can cause pulmonary congestion, and irritation to skin and eyes. Exposure of DBCP through food is low. Like 1,2,3-TCP, DBCP dissolves in water and sinks to the bottom of the aquifer. DBCP is usually removed from groundwater by professionals through filtration of active carbon, hydrogen peroxide combined with a catalyst, ozone, and zero-valent iron. Please do not attempt the removal of DCBP contaminated groundwater wells yourself. Contact a remediation specialist for help with any groundwater contamination issues. Hexavalent chromium, or Chrome-6, is a metal that occurs naturally as rock as Chrome-3, which is less toxic. Chrome-6 comes from chemical manufacturing and combustion of natural gas, oil, and coal. Chrome-6 has been detected in 2,475 California drinking water sources. The map shows active and standby California Department of Public Health wells with at least one detection of more than 1 microgram per liter detection limit for reporting. The maximum limit in drinking water is 50 micrograms per liter of total chromium. Exposure to Chrome-6 through breathing, ingestion, and contact with skin can cause cancer, reproductive harm, eye and respiratory irritation, asthma, damage of liver and kidneys, anemia, acute gastroenteritis and gastrointestinal hemorrhage, and convulsions. Chrome-3, which is less toxic, is naturally occurring and becomes Chrome-6, which is toxic, when it is oxidized or combines with oxygen. Chrome-6 is predominant in groundwater, which has conditions that is high oxidizing and alkaline or has a pH above 7. Chrome-6 can be reduced to Chrome-3 in the presence of organic matter like ferrous iron and sulfide. The drinking water in Hinckley, California, near Barstow in Southern California, was impacted by Chrome-6 as depicted by the film Erin Brockovich, where Pacific Gas and Electric, or PG&E, was found guilty of contaminating the drinking water with Chrome-6. Water supply is another challenge that persists in San Joaquin Valley's underserved communities, especially those that are groundwater dependent. Groundwater levels have been declining in California. Overpumping of groundwater led to more than 500 million acre-feet of groundwater being overpumped during the 2012 through 2016 drought. There are thousands of dry wells, and there are projected to be more than 12,000 more dry wells based on current groundwater sustainability plans to address groundwater overdraft under the Sustainable Groundwater Management Act, or SGMA. For more information on SGMA, watch Cali Water Ag's San Joaquin Valley Water and Land Use series. Surface water is also expensive and unreliable. The cost of water is unaffordable for many underserved communities in the San Joaquin Valley, already burdened with facing environmental issues, medical bills, and needing to purchase bottled water for drinking. The costs associated with addressing contaminated water in underserved communities varies, but on average, about $75 per month per house is used for bottled water. Point-of-use filters cost from $1,000 to $4,500 per unit per home for 1 year. A water tank is around $3,680 plus $900 for tank refills. The cost for water treatment systems and alternative supply sources vary, and prevention and remediation of contamination costs are unknown. The costs of addressing dry wells include the same costs of bottled water and water tanks as for addressing contaminated water. Lowering a well pump can cost anywhere from $5,000 to $10,000. Deepening a domestic well can cost $20,000 to $45,000, and deepening a community well can cost up to $1.5 million. Costs for maintenance and operation for community drinking water systems include treatment systems, storage tanks, distribution lines, well pumps, and meters, while costs for private domestic wells include pump repairs and maintaining point-of-use or point-of-entry filters. Other factors impacting affordability of drinking water are income level of residents, economies of scale, and the ability to spread cost across several homes. Local state support for drinking water solutions, regulatory requirements, external factors impacting water quality, and reliability. This picture shows Lanier residents Isabel, Lala, and Leticia standing in front of the non-operational arsenic treatment plant in their community. Here's an example of Lanier's arsenic treatment plant situation. The community got $1.5 million in federal community development block grant funding. Engineers constructed an arsenic treatment plant, but the plant was shuttered after only 4 months because residents simply couldn't pay for the high cost of operating the plant. The engineers had not spoken with the community adequately and had not understood how much water was actually being used and how much residents could pay. Eventually, the operators of the community water system got to a point where they could neither afford to keep the plant running nor pay PG&E bills that powered their well pumps, so they had to shut down the treatment plant. This example emphasizes the importance of communicating with the community and co-developing solutions for underserved communities with them, so that solutions are equitable and tailored to a community's needs. See Part 3 of this drinking water series for details on how to help and work with community members to help them solve drinking water and other environmental issues. In review, we learned that about 87% of unincorporated communities in the San Joaquin Valley depend on groundwater. Drinking water issues disproportionately impact low-income communities and communities of color. Community drinking water issues include water quality, water supply, and unaffordable costs. Thank you for tuning in. If you have any questions, please ask in the video comments or feel free to send an email to caliwaterag@gmail.com as seen on that screen. And don't forget to hit that like button, subscribe to Cali Water Ag, and share this video with family and friends so that together we can learn more about California water and agriculture. Special thanks to Vice Lab at UC Merced and Amanda Monaco at Leadership Council for Justice and Accountability for information and insights on drinking water issues present in San Joaquin Valley's underserved communities. Thank you to all the community members in underserved communities for their resilience and determination to fight for environmental equity and justice. and to all the community organizations that work hand in hand with community members to make it happen.